Welcome to The Explainer. Today, we are diving into a really fundamental concept in chemistry, one that explains something kind of weird, why some reactions seem to just quit before they're finished. We're talking about chemical equilibrium.
All right, so think back to your first chemistry class. You probably learned that reactants, well, they react to form products. And the whole thing stops when you run out of one of the starting ingredients. It's A plus B equals C, and that's the end of it. Simple enough, right? But what if it's not? What if some reactions get partway through and just stop?
To really get what I'm talking about, let's picture a classic experiment. Imagine a sealed glass vial. It's a closed system, so nothing can get in or out. And inside, it's filled with this dark reddish-brown gas called nitrogen dioxide. This is our starting point. Now, this nitrogen dioxide has a neat trick. It can react with itself to form a totally different gas, dinitrogen tetroxide, which is completely colorless. So just like we'd expect, when the reaction kicks off, that dark brown color in the vials starts to fade. It gets lighter and lighter. And here's where it gets strange. It never goes completely clear. After a little bit, the color just settles. It becomes this constant pale brown. To the naked eye, it looks like the reaction just gave up. It's done. So what on earth is going on here? Well, that observation, that moment where it seems to stop, it's not a mistake. Actually, it's the experiment working perfectly. It's showing us a core principle of how chemical systems find their own unique balance point.
This stop state actually has a name. It's called chemical equilibrium, and it's defined as the point where the concentrations, the amounts, of all your reactants and your products just stay constant over time. But, and this is a huge but, constant does not mean static.
This brings us to the most incredible part of this whole story. On the surface, everything looks perfectly still. But if we could zoom in to the molecular level, we'd see it's an absolute frenzy of activity.
This is the big reveal. It's called a dynamic equilibrium. The reaction hasn't stopped at all. What's really happening is that the forward reaction, our brown gas turning colorless, is still chugging along. But at the same time, the reverse reaction, the colorless gas breaking back down into the brown gas, is also happening. And crucially, they are happening at the exact same speed. It's a perfect, non-stop molecular balancing act.
If that feels a little abstract, think about it like this. Picture a giant stadium with thousands of fans. At any given moment, you might have, say, 17,600 fans in their seats and 400 people out getting snacks. Now, people are constantly moving. Someone leaves their seat to get a hot dog, and at the same moment, someone else returns to their seat. The individual people are always changing, but the total number of people in the seats and at the concession stays exactly the same. The system is active, but the overall numbers are stable. That's dynamic equilibrium. Okay, so this whole idea of a dynamic balance, this back and forth, it only works if the reaction can actually go both ways. And that brings us to a really cool class of reactions that can literally run forwards and backwards. We call these reversible reactions. They're chemical processes that don't just go one way. In an equation, you'll see them marked with this special double arrow instead of a single one. It's a signal that as the forward reaction creates products, those very products start reacting with each other to reform the original reactants. And that point of equilibrium? It's simply the moment when the speed of the forward reaction perfectly equals the speed of the reverse reaction. So this begs a really interesting question. If a reaction can go forwards or backwards, does it matter where you start? Do you end up at the same point? Well, let's take a look at the data. And the answer is pretty amazing. Check this out. In the first experiment, we start with a bunch of the colorless gas N2O4 and 0 of the brown gas. In the second experiment, we do the complete opposite. We start with only the brown gas, NO2, and none of the colorless one. But look, just look at where they end up. The final concentrations are exactly the same, down to the third decimal place. It doesn't matter which direction you approach it from, the system finds the exact same balance point. And this observation leads us to a really fundamental law of chemistry. Basically, for any given reversible reaction, as long as you keep the conditions the same, there is one and only one set of equilibrium concentrations. The destination is always the same, no matter the starting point. Okay, so knowing the concept is one thing, but how do chemists and engineers actually predict and calculate these final amounts? Well, they use a surprisingly simple but really clever organizational tool. It's called an ICE table. And the name is a super helpful mnemonic, ICE. I stands for the initial concentrations you start with. C stands for the change that happens as the reaction moves towards equilibrium. And E stands for equilibrium, which is the final state you're trying to find. It's just a way to keep all your numbers straight. So here's how you'd set one up. Your I row is just what you put in the vial at the very beginning. The C row is the magic. We use a variable, we'll just call it X, to represent how much the reaction shifts. So your reactants get used up, meaning their change is negative X. Your product gets made, so its change is positive. And see how it's plus 2X for the product? That's because the balanced equation shows we make 2 of them for every one of the reactants we use. The E row is just the I row plus the C row. It gives you the final answer. And let me be clear, this is not just some abstract homework problem. ICE tables are an absolutely vital tool in the real world. Think about making fertilizer on an industrial scale. To maximize your output and make the process profitable, chemists have to be able to predict exactly how much product they're going to get. Understanding equilibrium isn't just cool science. It's a multi-billion-dollar business. So, to wrap this all up, I'll leave you with a question you can now totally answer. Think about a sealed bottle of soda pop. It is a closed system, and there is a dynamic equilibrium happening right inside. Can you figure out what it is? And, more importantly, what happens to that perfect equilibrium the very instant you twist that cap and hear that fizz?